Mercury, an enigmatic planet, despite being closest to the Sun, is still the least known to us. Often overshadowed by its neighbors, it's a world of mystery waiting to be revealed. What if Mercury isn't what we thought it was? Recent discoveries indicate that this planet is more dynamic and complex than anyone imagined. From shrinking landscapes to mysterious blue troughs, Mercury is challenging everything we know about it. Imagine a planet rushing around the Sun at breakneck speed. A world so close to the solar furnace that it's hard to even get close to it. Few missions have dared to visit this elusive world, and those that have discovered only glimpses of its secrets. However, a new mission, Bepicolombo, is on its way, and it promises to unlock mysteries that have puzzled scientists for decades. Already, we're seeing things that defy explanation: strange features, unexpected phenomena, and hints of a story yet to be told. Mercury's X-ray auroras, its changing topography, and its hidden interior all suggest that the planet is far more intriguing than we ever thought. Prepare to see Mercury in a whole new light. It's not just a planet, it's a mystery at the edge of the Sun. What is Mercury? Mercury, the innermost planet, orbits closest to the Sun. It's the smallest planet, slightly larger than our Moon, and takes only 88 Earth days to complete one orbit. Because of its proximity to the Sun, Mercury experiences temperature extremes that range from scorching highs of 800 F to icy lows of 290 F overnight. Its surface is a mosaic of craters, ridges, and plains. Unlike other planets, it has no significant atmosphere to protect it from meteoroids, resulting in a landscape heavily riddled with craters and reminiscent of our Moon. One of the most striking features is the Caloris Basin, one of the largest impact craters in the solar system. This massive basin, about 960 miles in diameter, was formed by a colossal impact early in Mercury's history. Another unique aspect of Mercury is its unusually large core, which makes up about 85% of the planet's radius. This iron-rich core generates a magnetic field, but it's only 1% as strong as Earth's. Despite its weak magnetic field, Mercury has magnetic poles and a magnetosphere that interacts with the solar wind, creating phenomena such as the recently discovered X-ray auroras. Exploring Mercury presents significant challenges. Mercury's proximity to the Sun means that spacecraft must withstand intense solar radiation and heating. In addition, Mercury's fast orbit requires precise and energy-intensive maneuvers to enter its orbit. In 1973, NASA launched Mariner 10, the first spacecraft to visit Mercury. Mariner 10 utilized the gravitational assistance of Venus, allowing it to make 3 flybys of Mercury between 1974 and 1975. These flybys produced the first close-up images of the planet's surface, showing the heavily cratered terrain and complex geologic features. The spacecraft's images showed a world similar to our Moon, with vast plains and numerous impact craters. However, the mission captured only 45% of the planet's surface, leaving much unexplored. Despite the limited coverage, the mission data laid the groundwork for future research. Decades later, the Messenger spacecraft, launched by NASA in 2004, became the first spacecraft to orbit Mercury. After a challenging journey that included flybys of Earth, Venus, and Mercury itself, the spacecraft entered its target orbit in 2011. During its 4-year mission, Messenger made more than 4,000 revolutions around the planet, collecting a wealth of data on its surface, composition, and magnetic field. Messenger showed Mercury's surface in unprecedented detail, mapping almost the entire planet. It revealed volcanic plains, evidence of past tectonic activity, and gave a glimpse of the planet's thin exosphere. One of the most surprising discoveries was the presence of water ice in permanently shadowed craters at Mercury's poles, even though the planet is so close to the Sun. Building on the successes of Mariner 10 and Messenger, the Bepicolombo mission represents a significant step forward in Mercury exploration. The mission is a joint effort between the European Space Agency (ESA) and the Japan Aerospace Exploration Agency (JAXA). Launched in 2018, but Piccolombo aims to provide comprehensive data on Mercury's geology, atmosphere, magnetosphere, and history. But Piccolombo consists of two main spacecraft, ESA's Mercury Planetary Orbiter and JAXA's Mercury Magnetospheric Orbiter, also known as MEO. Together, these spacecraft will study the planet from different perspectives, offering holistic views of its evolution and environment. The mission's journey to Mercury is long and complex, involving many gravity assist maneuvers. But Piccolombo has already made flybys of Earth in 2020 and Venus in 2020 and 2021. It will make 6 flybys of Mercury before entering orbit in December 2025. These flybys are critical to adjust the spacecraft's trajectory and slow it down enough to be captured by Mercury's gravity. The goals of Piccolombo are ambitious. The mission aims to map the planet's surface in high resolution, analyze its composition, and study the magnetic field and magnetosphere. It will also study the planet's exosphere and search for evidence of past volcanic and tectonic activity. Using orbiters, scientists hope to gain new insights into the formation and evolution of Mercury, as well as its mysterious magnetic field. Piccolombo, since its launch in 2018, Piccolombo has been steadily approaching Mercury, making a series of flybys that have already yielded significant results. These preliminary observations provide new insights into Mercury's complex geology and dynamic environment. One of the key contributions of the mission was the detailed mapping of Mercury's surface. The spacecraft discovered many previously unknown craters, each telling a different story of the planet's turbulent history. Among them are impact basins that show the scars of ancient collisions, shedding light on the early chaotic period of the solar system. One of the mission's most intriguing discoveries is the detection of X-ray auroras around the planet. Unlike visible terrestrial auroras, Mercury's auroras are detected in the X-ray spectrum. This phenomenon was first hinted at by the Messenger mission and is now confirmed by Piccolombo. These X-ray auroras are caused by the interaction between Mercury's magnetic field and the solar wind, a stream of charged particles emitted by the sun. When these particles collide with the planet's surface, they generate X-rays, causing a faint but scientifically valuable glow. This discovery not only confirms the presence of a magnetosphere, but also provides insight into the nature of Mercury's magnetic field and its interaction with the solar wind. Mercury shrinks. Another important recent discovery was confirmation that Mercury continues to shrink. High-resolution images have revealed features such as lobate scarps and wrinkle ridges, which are formed by the compression of the planet's crust as its core cools and hardens. These results build on observations made by the Messenger mission and provide clearer evidence of Mercury's ongoing geologic activity. The planet's compression has caused its radius to shrink by several kilometers since its formation, creating stress cracks on the surface that manifest themselves as ridges and cliffs. Piccolombo, in turn, has identified several regions where this contraction is most obvious, providing a unique opportunity to study planetary geology in real time. These regions reveal not only Mercury's cooling history, but also its current state, giving scientists clues about the planet's internal structure and thermal evolution. At first glance, Mercury's heavily cratered surface resembles that of our Moon. Both bodies are riddled with impact craters, indicating a long history of collisions with asteroids. Mercury's surface, however, a closer look reveals significant differences. Mercury's craters are often interspersed with ridges and fault scars, which are less common on the Moon. These scars are indicative of Mercury's compression, a process not observed on the Moon. In addition, there are areas on Mercury's surface with fewer boulders than on the Moon, suggesting different geologic processes. One of Mercury's most enigmatic features is its depressions. First discovered by the Messenger mission, they are irregular, shallow depressions, often surrounded by bright halos. Their formation has puzzled scientists since their discovery. Initially, researchers hypothesized that these depressions might be of volcanic origin. They considered the possibility that volcanic processes had left behind these unusual formations. However, the distinct appearance of the depressions and the lack of associated volcanic features prompted further investigation. According to current thinking, Mercury's troughs were formed by sublimation, a process by which solid materials are converted directly into gas. This process probably involves volatiles beneath Mercury's surface. When these volatiles sublimate, the surface erodes, forming sinkholes and the bright halos seen around the depressions. These data suggest that, despite its proximity to the Sun, Mercury stores volatile compounds just beneath its surface. Continued sublimation and the formation of depressions indicate that the planet is still a geologically active world, contrary to previous assumptions.